Let's take a look at an important theorem here. This theorem is going to show that a particularly important linear transformation is a linear transformation. So let's let V be an n-dimensional vector space. Let's let B be an ordered basis for vector space V. We're going to be interested in the transformation that maps vector space V into Rn, given by the transformation of V is going to be equal to the coordinate vector of V with respect to basis B. So we want to prove that this is a linear transformation. Okay. Now, actually, the very first thing that we should double check here is that this is well defined as a function. So what do I mean? So generally, let's take an example here. Let's say S is a mapping from a vector space. Let me pick a different one so we're not confused. This is an example of why we need to be careful here. Vector space W to R. Actually, let me be a little clear here. Let's say R2 to R3. Okay. Defined by S of xy equals A1, B1, sorry, A1, A2, A3. If xy is equal to A1 times 1, 0 plus A2 times 0, 1 plus A3 times 1, 1. Okay? So the transformation is just going to be the coefficients of the linear transformation that equals xy. Okay? Problem is, this is not a well-defined function. What do I mean? Let's take a look at an example so I can illustrate. Let's take a look at t. Let's take a look at a very simple example, t of 1, 1. Okay? Well, of course, I can make my coefficients 0 for A1, 0 for A2, and 1 for A3, right? 0 plus 1 times 1, 1 is equal to 1, 1. Okay, so 0, 0, 1. Okay, but also transformation of 1, 1. I could also, sorry, not t, I'm using letter S, aren't I? Let me be consistent here. S of 1, 1. I could also use coefficients 1, 1, 0. Because 1 times vector 1, 0 plus 1 times vector 0, 1 plus 0 times vector 1, 1 is also equal to vector 1, 1. Okay? The problem, though, is these are not equal. So we're not even concerned at this point with whether this is a linear transformation. It's not a transformation. It's not a function. One of the properties of a function is that when you evaluate a function at an input point, you're only going to get one output. And here we're getting two different outputs. S is not a function. Okay? So this shows you the dangers of just defining something and assuming it's a function. So the very first thing we're going to do here is show that t is a function. Okay, First, we will show t is a well-defined function. Note t of v is equal to the coordinate vector of v with respect to basis b, which remember is just the coefficients of the linear transformation. Okay? It's just the coefficients of the linear transformation of the basis vector. Okay? A1 to AN, that's the components of the coordinate vector. Okay? But B isn't just any spanning set of vectors, it is a basis. They are linearly independent. And we have previously proved that the expression of a vector v, the linear combination of vectors that gives me vector v, is unique. There is only one set of coefficients that will make this work if the vectors are a basis. Since B is a basis, the linear combination, we say the coefficients of the linear combination is unique, meaning T is well defined. Okay? And actually, let me say is a well-defined function. Okay? So this is similar to the example we just showed, but in the example we just showed, the vectors we had didn't form a basis, right? These vectors do form a basis. And so when we are taking a linear combination of a basis, the linear combination is unique. There's only one way to combine a basis linearly, or actually any set of linearly independent vectors, to get a particular basis, particular vector v. Okay? All right. So that was probably a little confusing, but hopefully it makes a little bit of sense. Okay, we just need to check that the thing we're calling a function is actually a function. The rest of the proof is very straightforward. We're going to check the usual things we check for a linear transformation. Now that we know it is a transformation, that it is a function, we need to check that next, let's check that the transformation of k times a vector v is equal to k times the transformation of v for any v in the domain and any scalar k. All right? So let's let v be this particular linear combination of the basis vectors. Then the transformation of k times vector v is going to be the transformation on k times, and I'm just going to swap out v with its linear combination of vectors here, a1 v1 plus dot 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 plus an vn. I'm going to go ahead and distribute the k into the linear combination. So I get ka1 v1 plus, and keep on doing that till I get to the last one. So each coefficient gets multiplied by k, right? Now let's go ahead and take the transformation. Now, the transformation here, remember, is going to be the coordinate vector of the vector inside, which is just going to be the coefficients of the linear transformation of these basis vectors, right? So the coordinate vector here, well, the first component of the vector is the first coefficient of the linear combination. The second component would be the second coefficient of the linear combination, and so on, until you get the last coefficient in the linear combination of the basis vectors of vector b. Okay? But now this is just a vector in Rn. So I could unscalar multiply scalar k. And a1 to an, that's just the transformation on vector v, because these are the coefficients in the linear combination that give me vector v. So this is just going to be k times the transformation on v. All right, so that proves this condition. Okay, transformation of kv, if we follow the equal signs, it's equal to k times the transformation of v. Okay, we have one more property to check. Next, let's show that the transformation of sum of vectors is equal to transformation of u plus the transformation of v for any vectors u and v in vector space v. All right, so I'm going to start by defining the linear combination of the basis that gives us vector u, that gives us vector v. Okay, so u is equal to, let's say, well, maybe I'll define v first, just to be consistent here. a1 v1 plus dot 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 plus an vn. And let's let u be b1 v1 plus dot 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 plus bn vn. Okay, and we just do like we did last time, plug in. Transformation of v plus u is equal to the transformation of, well, v is a1 v1 plus dot 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 plus an vn. Just replacing a with its linear combination. And similarly, we're going to replace u with its linear combination. So u is b1 v1 plus dot 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 plus bn vn. Okay, now let's add like terms together. a1 v1 plus b1 v1 is a1 plus b1 v1. And I could keep doing that until I get to the very last term. Last term, if I add the vn terms together, I get an plus bn vn. And so the transformation on this, I just get the coefficients of the linear combination. So this is going to be the coordinate vector of the sum of those two vectors with respect to basis b. Okay. But now I can break these up into two vectors, since this is just a traditional Rn vector space now. So this is vector a1 to an plus vector b1 to bn. And a1 to an, that's just the coefficients of the linear combination of the basis vectors that gives me v. b1 to bn is the coefficients of the linear combination equation that gives me u. So put them together, the a1 to an, that's the transformation on vector v, because it's the coordinate vector of v with respect to the basis. b1 to bn, that's the coordinate vector of u with respect to the basis. And so I've shown that the transformation of the sum is equal to the sum of the transformation. So T is a linear transformation.